To most people who have been in like any kind of embeddings work or search work, I think, nodes does not really need an introduction. I think for the past couple of years, I've joked that a lot of the cutting edge RAG work that people are doing now just felt like a lot of my intern projects when I was fine tuning embeddings in like 2017, 18. And a lot of that was hoping that we could like average word to vec vectors in a sentence using GenSim and hope that things worked well, or use some topic modeling. And it was in 2019 when you dropped sentence transformers and sentence BERT, and it kind of really made a lot of things click in terms of how we can process a lot of text. And at that time, I was searching over comments and product feedback and product descriptions. Um, and then since then, you've also sort of co-authored Beer and MTEB, which is basically the benchmarks that we all quote when we look at how models perform across multiple domains and languages. Again, like a very core part of embedding models. And next week we'll have Chroma talk a little bit more about how they do generative evals and create their own personal benchmarks rather than using MTEB. But generally, I think there's been a few people that I know that have sort of worked on semantic search for this long. And now you're the VP of AI search at Cohere. You just shipped the Embed 4 models, which is my understanding is it's going to be long context over images and text. And I think one thing to call out to a lot of people who I worked with in the past, which is that historically there were things like clip style embeddings, but they were really much trained on captions. So you could find a picture of a giraffe or a picture of a red car, but it would never work on things like tables and charts and diagrams. And I think Embed 4 and these kinds of models is the first time I've seen them really work at a very large scale. And so I'm really excited to welcome Nils to present. And so the stage is yours.
Oh yeah, happy to be here. So in the talk, I will talk about like text RAG, vision RAG, embed 4, challenges on vision LMs, and like talk lightly on how we operate and how we work as a team to train like these foundation models, but then also looking forward to questions you have at the end to dive deeper on like sections you find interesting. Bit on the background. So at Cohere, what we do is like we train these foundation models. So we train foundation models for generative or command model, foundation models for embeddings and re-rank, which is my line of expertise. And then we specialize in like these secure enterprise deployments. So we target enterprise customers, often in like the most regulated industries like healthcare, banking, telecommunication, critical infrastructure, and then bring these technology into the environment. And what me and my team are working on is like these Compass products, so the intelligent search and discovery product. And it works extremely well. So it's built on top of like the different models, has several more models included, but you really see the difference if you do like a comparison against embedding. So sadly, a lot of people like still in the field just do embeddings. They think, okay, that's like the golden egg. That's what we can use for everything. But you really see the difference between kind of like an embedding solution and like a fully fledged enterprise search solution. So here we have like some enterprise data. It has invoices, tabular data, and some scanned documents. And then if you start very simple, like which products did Jenkins buy from us, and you search over invoices, you see with an embedding model, it's not able to find Jenkins, so it finds Cox Moore, and then also goes further like Combs and Hinton and Atkins. So find like all type of invoices, but not from like the Jenkins one. And then the fully fledged like finds the right information. Similar, it's also interesting to see like understanding of dates. So if you have like a rack setup and say, hey, list me all invoices from 2016. Again, just an embedding approach gets you an invoice from 2018 and 17 and 17 and 21. So it's not really able to like understand that you have like a date of issue. And then if I say, hey, list me all the invoices from 2016, then I have to look at like date of issue and need to understand like 2016. Similar, if it goes into like more complex, nuanced information. So you say, hey, what's the GDP of Germany? Again, embedding models are like very, very coarse-grained, topic-driven. So you ask like, hey, what's the GDP of Germany? And then you see here, oh yeah, it has a lot of like GDP included, GDP rank, GDP growth, GDP per capita, and so on. But sadly, that's about the economy of India. And so it's not a good fit. I asked like what's the GDP of Germany? And you go down, like you see economy of China and economy of United States and Russia. So it finds all the GDP heavy ones, but not like the GDP of Germany. And for example, what we did is like a lot of like table understanding. So table understanding is often like a two-dimensional thing. You need to say, oh yeah, I have like a row with Germany, I have like some header with GDP, and then you find the right information. So in Embed 4, we focus on like multimodality. So still in enterprises, you have like these lawsuits. Here's like a lawsuit from the early 2000s against the tobacco industry in the US. And then if you say something like, hey, did customer raise concerns about negative health effects of cigarettes? You see when you use, for example, here the Google Clip model or the OpenAI Clip model, it finds something for smokers, but like, hey, uh, thank you for participating in the smoker survey. It's great. Here's your bonus. And it's not really like finding a document with negative health effects. While in Embed 4, we see like here we have like the handwritten, and then the customer says, hey, the issue is one of life or death, cancer. So raises concern about cancer and then that cigarettes causes cancers. Cool. So yeah, we constantly kind of like push the retrieval space as it's like an enterprise uses. It's extremely critical that you connect to the enterprise use case. And if you really just use embeddings, it's like, yeah, maybe catch up on like the topics and see like how the field evolved. And we kind of constantly push. So we started with like English paragraphs, multilingual paragraphs, support for like large corpora, 100 billion of documents, structured data, tabular data, low resolution images, text and image inputs, search with conditions like negations, ranges, long text documents, high resolution images, scanned documents in handwriting. So we always see like, okay, what's like the next challenge? How can we tap them in and how can we address it? And you really, if you want to build like really good RAG solutions, in our experience, it often breaks down on the retrieval part. So the generative models, they're all very good, like whatever your flavor is. If you use OpenAI or Gemini or Qwen or Llama, they are all very good, but it often breaks on the retrieval part. You retrieve shit, you present shit to the LM is producing shit output. And then the user is complaining and say, hey, why is the solution so bad? Cool. So today I want to talk about like from text RAG to vision RAG. So very traditionally, we have like these text RAGs. So number one use case in enterprises is PDFs. And we know PDFs have tables, and we got like very creative when we design these tables in PDFs. And then we use some parser like Markdown or Docling or unstructured. And then we convert this to a Markdown format. And then often you see, for example, with tables, a format like this, where you see like columns are shifted, rows are shifted. You do text embeddings, you do text LM. And then if you ask like a question, hey, what's in this case, it's like the federal tax rate for small businesses in 2014. The text LM sees something like this, picks the wrong column, picks the wrong cell, produces the wrong output. And again, you lose the trust from the user. You say, okay, this system is saying you have like a 3% text rate, but in reality, it's maybe like an 11% text rate. So I'm not trusting the system. And then very often, like in many cases, when you trace it back, you see that these parsing step breaks, that it doesn't understand the table because people thought like multi-column, multi-row headers is a good idea. Even worse, some customers have images like this. So this is from like a Boeing manual where they kind of like put like a diagram. How does a Boeing look from the inside? And the question is like, okay, how do you convert this to Markdown? I saw some models trying to do like ASCII arts. Some are really just extract the table. That's not really helpful. So when I say, hey, where's the fire extinguisher? Where do I find it? It's not really helpful to say, oh yeah, I find that there's fire extinguisher, but I need to like read the image and understand the image. And so one trend, which are very exciting, is like going from text RAG to vision RAG. So text RAG is these original PDF to Markdown, getting some Markdown, doing some text embedding, doing some text LM, and then you get like the question like, hey, where's the fire extinguisher? Vision RAG makes it so much easier. You just take the page as an image, you get an embedding of the image, you put it to the Vision LM, and then the Vision LM can reason on this. And in terms of code, it's quite simple. So here's like a Colab notebook of Cohere Embed 4 and Gemini Flash. So you set up the respective API keys, and then you say, okay, I have like different images I want to embed. So here's like several images on financial incomes from different companies. You download the image, you get like a base 64 representation of the image, you send the image to the endpoint, you get the embeddings back, and then at search time, you embed your question, you get the embedding for the question, you do like a vector search over the image embeddings and your query embeddings, and then you get your most relevant image, and then you send this to, in this case, to Gemini or GPT-4o or Qwen Vision and say, hey, answer the question based on the following image. Don't use Markdown. Please provide enough context for your answer. You say, okay, this is the image, and that's my image. That's my question. That's my image. And it works really well. So if you say, hey, what's the net profit for Nike? First retrieval step finds this image, and then the LMs can reason on it and say, hey, according to the Nike income statement, the net profit is 0.8 billion. You can also do a bit more complex, like what are the 3 largest acquisitions from Google? So it's able to read these information from the image, like Wiz, Motorola, and Mediant. So it's even like able to understand the logos. So you don't have to ensure, for example, like in a PDF to Markdown, you would need to ensure that logos are translated correctly, which can sometimes be a problem. Like if there's just like the Apple for like the Apple company, you're not really be sure that the PDF to Markdown extracts the right name for the company. Similar, you can also reason on the image. So if you have something like what would be the net profit for Tesla without interest, again, you find the right image, and then you see the LM, hey, based on the income statement provided, the net profit is 0.4. The diagram shows interest is 0.3 billion flowing into the net profit. Then do the math, 0.4 billion minus 0.3 billion. So it's 1 billion. So the profit for Tesla without interest would be 0.1 billion. So it's like a very, very cool system. It's like very easy to use. And especially if you have like any of these complex visuals, it's like very nice to reason on them. You don't have to have the headache, like how do I take this, put it to Markdown, do all the lines, do all the colors, and all preserve it. So it extremely simplifies your RAG system. To give you a bit more history on vision embeddings, how they work and how they evolved over time, and like, yeah, what's the history on that? So in early 2021, OpenAI published CLIP, which became quite well known. So CLIP is like 2 models. You have a text model and you have an image model. And then taking the text projected to a vector space, taking the images projected to an image, also to the vector space. And yeah, as you said, Jason, in the beginning, it was trained mostly on like image catch, and this is a cat sitting on a bench. The text was like restricted to like 70 tokens, was terrible text-to-text search. Low resolution images had just like 224 pixels, so only cat images were possible, but not really like complex text images. And you have like these modality gaps. So you see like all the text is here and all the images is here. So if you do like a text to image search, that's okay. But in enterprise, you often have like a mixture of modalities in your corpus. So in your corpus, you have maybe some text documents and you have like some image documents. And then if you ask a question like, hey, what's the market share of AWS? and put it into the OpenAI Clip model, it will retrieve JP Morgan Chase is leading the US banking sector. And you're wondering like, hey, why is it not retrieving like these nice infographic? And the reason is because of like these modality gap, like all the image embeddings and all the text embeddings are like very, very far away. And so what we worked on in Cohere Embed v3 is to align the vector spaces. So first make the text search really good, up to 512 tokens, ensure that the text search across languages works extremely well, increase the resolution to 336 tokens. It's better, but not great. And especially solve the modality gap. So if you now go in and say, hey, what's the market share for AWS? We find you the image with the AWS market share. If you ask about the market share for JP Morgan Chase, it will find you the text document for this. So this was good for text and small images up to 336 pixels. But obviously we wanted to aim higher. And this is like what we worked on like in Embed 4. We support high resolution images up to 1800 times 1300 pixels. What's interesting, you can interleave text and images. So before it was always either text X or one image. So input a text or an image. But now we can interleave text and images. So if you think about like a markdown, you can have text and images interleaved. OCR-free text understanding in images in 100+ languages. So you don't need to do OCR. You can just say, okay, this is my image, my handwriting, and I search on this. And we also extended the context length to 128K tokens, which will be quite critical to really understand or be able to understand these high resolution images. There are various use cases which are very cool. So one is like scanned documents. It used to be always terrible to work on scanned documents, but now you just present the images of the scanned documents, embed them and find them. Similar, we know these whiteboards. So we're like you're at an offsite, you write it down on the whiteboard, you take a picture. And that's like always like very hard to search on the text. But here you can like search on the text and say, okay, what's the ground rules we defined in the offsite? Also in e-commerce, nice use cases like in e-commerce, you have product images, several product images, you have a product text, a title and a description. And before that, it was like always hard, like you have 5 product images and a product description. So yeah, like 6 embeddings, and they did not match well together. But now you can just pass it in as one, and then it produces for this embedding that stores information across image and text. So for example, from this image, we know the jeans is blue, but we don't know it's a Levi's 501. From the product text, we know it's a Levi's 501 jeans, but we don't know it's a blue jeans. But if you pass both in, you get like one embedding for like a blue Levi's 501 jeans. So it's taking information from the image and information from the text together, blends it together and produces good embedding output for that. Something I really liked is these prompted image search. So imagine you spend your vacation on like a nice range in I don't know, in Canada. You saw like a cool cowboy wearing a nice cowboy hat. You snap the picture and say, hey, the hat, please find me this hat in green. And then this is like for a real customer. It goes over the product catalog and then says, okay, in our product catalog, this is the most similar hat we have in green. And so it's like very nice when you can go in, take the image, describe how you want to change it, and then search over the text and images you have. Cool. Want to cover a bit on like vision LLMs, how they work, how they operate, and then talk more on challenging like scaling the resolution. So for us, the most critical was like to scale the resolution. As mentioned, the first vision LLMs, they had like very low resolutions, like 200 or 300 pixels. If you take like a PDF page and yeah, convert it to like these 200 pixels, it's not readable anymore. So you lose all the information if you run at like low resolution. So how how these vision transformer work is they take take an image and break it down into patches. So patches is like small sub-images, totally 14 by 14 or 16 by 16 pixels. And then you linearize these sub-patches, and then you add some position information. So you say, okay, this is patch 1, 2, 3. So you kind of like count from 1 to 9, and then you put it into like a standard transformer model. The latest vision transformer, like SIGLib, they can handle up to 500 times 512 times 512 resolution, which is 1024 tokens. But again, 512 resolution is like very, very hard. So this is a PDF page from the SIGLib 2 paper, resized to 512 pixels. Can still read it, but it's not really enjoyable to read it. And if the text gets smaller, it's like very hard or impossible to read it. And obviously, if you present an image to an embedding model where the embedding model is not able to read the text, it's not able to produce good embedding. So if you cannot read it, you can't produce an embedding. And so one big challenge is like, how do you increase the resolution? The resolution scales the tokens quadratically. So if you go, let's say, 2000 times 2000 pixels, that would be like 20K image tokens. And there's like no pre-trained vision transformer available for this resolution. In general, like pre-training is seldom done at like 20K context lengths. I mean, from TextLM, we know they claim, I don't know, 100K, 200K, 1 million, 10 million context lengths, but none of them has been trained at like these context lengths. So if we look at like Qwen3, they pre-trained at like 4K tokens, and then using tricks to extrapolate the longer text. So go from like 4K text tokens to like, I don't know, 128K tokens. But these extrapolation is not really possible for images. So for text, I can take the first 4,000 tokens and then predict the token 4001. But when I take an image and I resize it to 512 pixels, information gets lost. So these kind of like, I just use fewer image tokens is not really possible with images. But the research community has been quite smart how to scale vision transformers, vision LMs to higher resolutions. So one paper I really like is the mini CPM. They have a vision transformer again with like standard low resolution 384 times 384 pixels. And then they take full text, a full image, and resize it to like these small resolutions. So take this big image and create like a resized version of it. But then they also create like smaller sizes at 384 pixels, like A to F. So they have kind of like a sliding window over the image. And so the one image becomes 7 images. The 7 images are encoded individually with the visual encoder. And so at the end, you end up with like 7 patches times 1024 tokens each. So this one image is encoded as like 7K image tokens. And then what they have is like these compression layer. So as an input, it gets 1024 input tokens and outputs 96 output tokens. So at the end, this image would be encoded as 670 tokens, which is then sent to the large language model. So one image becomes 670 tokens, and then it goes to the LM, and then you can ask the LM to, hey, describe what happens in the image, or how many caps do you see in the image? And then the LM can reason on these 670 tokens. Second approach, which was made popular by Qwen2 Vision, is kind of like sliding windows. So with the mini CPM approach, you have like this issue that you resize the image. So you always force it to like 384 times 384 pixels. So even if the resolution and the scale is different, you resize it. So text can become like very blurry and strange. Like if the scale and the ratio between width and height of the image is changing, you get like very weird image looking. And then you have like these individual patches. And what Quen is doing is they don't resize, but they take the big image, and then they create like these smaller image tokens, like these 14 times 14 patches. And then they use window attention. So they don't do like a full attention over all these patches, but they take like smaller windows of 112 times 112 pixels, and then compute like the vision transformer on these individual small patches on these individual windows. And then they just have like 4 layers that employ full attention across all images. So this idea is a bit inspired from us humans. We also don't see an image all at once at super high resolution, but we have kind of like, we can scan over. So we take our eyes, we scan over the image, and then see individual things in high resolution. And then with the full attention across all image tokens and a few layers, you're able to scale and get like global image understanding. Training vision embedding models is, yeah, surprisingly not that difficult. So that idea is quite easy. So you have these query document pairs. So you have a query revenue of Nike in 2025, and then you have an image where you say this image is like a good fit. And then you put this to a vision LM, vision transformer. It's outputting you an embedding, and then you get like the query embedding and the document embedding, and then you force them to be close in the vector space, while negative documents should be distant in the vector space. So the idea is quite easy how these systems are trained. But the challenge is like the scale. So with embed 4, what we wanted is like 0 to n text and 0 to n images on query and document side. So the query side can just be a text, or it can be a text and images, or a text and multiple images. Same on document side, it can be just a text or just an image, or many, many texts and many, many images. And we wanted to make it like suitable for like text to text search, text to image search, image to text search, image to image search. We wanted to make it suitable for like multilingual, like 100 languages, cross-lingual. So let's say your documents is an Arabic PDF image and your query is Chinese, and then you're able to like search in Chinese over the scanned documents you have in Arabic. And yeah, it added a lot of like complexity. So each time you add like a new dimension to it, the number of combinations scales. We built a lot of evaluations. So at some point we broke Google spreadsheets. So we're running out of columns to put numbers in. We built evaluation for everything. So we had to test like for all these things. For example, one test is like how well can the model find information if the text in the image is really tiny. So we tested like different font sizes, going from like 50 point font and going all the way down to like 1 point font size, to then see, okay, how is the performance doing? And then you do the same, like, okay, if I search in English and my document is in Arabic, can I find it? If my query is a Japanese note I written on a napkin and I have like English documents as text, can I find it? So we build like hundreds and hundreds of training data sets with billions of these query document pairs to really test for all these type of things that people could imagine. Font size, font colors, font types. Like if you do very strange font types, is it able to find it? If you put it into a handwriting, is it able to find it? Is it changing if the text is black and the white background is white, or if you inverse the colors, or if you make it really colorful, like I don't know, if all your text is like rainbow colored, is it still able to find it? So yeah, we spend a lot of like evaluating, testing, uh, improving training data, and infrastructure became also a challenge. So training text embedding models is comparably easy. So if you take a text training corpus, it's maybe, I don't know, 10, 50 gigabytes of data. And so our GPU neural nodes, they have like roughly a terabyte of memory. And it's very easy. You take like all the 50 gigabytes of text data, you put it into memory. You have a terabyte of memory, so it's not a problem. But with these images, because images are so big, and especially if you kind of like unpack them back to like these patches and bitmaps, you have hundreds of terabytes of data. So you quickly run out of like memory. You have to think about like your infrastructure, about your nodes, how to distribute it, how to move data around, what to load from object storage, what to load from disk, what to put into memory. So a lot of like work on optimizing and getting like a really high throughput so that you can iterate well and quickly over these billions of query document pairs you created. Cool. To summarize Vision RAG, so the Pro is very nice. So you have no longer complex PDF to Markdown pre-processing. You just take the PDF, you take an image of the PDF, how it's shown to you as a user. You take that image, get the embedding, and then send that image to the LM. It captures all these visual complex information like tables, figures, charts that are very hard to convert to text. But there's also still some cons. So I think these are things we will be able to solve in the near future. It's slower and more expensive. So one page as a text is about like 500 to like 2000 tokens. But if you take a page as an image with a resolution of 1800 times 1200 pixels, that's 11K image tokens. So it's yeah, 10, 20 times bigger, meaning running the LM is like 10, 20 times slower. It's 10 to 20 times more expensive to do this on the vision domain. You also see higher rate of hallucination with vision LMs. So typically, LMs became very good, like very low hallucination rates on text inputs. But if you say, okay, here's my PDF, you have the 10 pages, and every page is an image, you still see that vision LMs hallucinate, produce wrong information, reads wrong numbers, and yeah, invent stuff that's not in the paper. But I think these are things that are solved. So vision retrieval works extremely well. Vision LMs, as of now, as of today, have limitations. They work really well if you have like these single image inputs, like, hey, what's the net profit for Nike? You retrieve one image and then ask the LM for that. But they don't work well yet on these. I have a question, I retrieve 10 images, I send 10 images to the LM and then hope for a question and answer distilled across these images. Because LMs, vision LMs, are still too slow, too expensive, and hallucinates too much. But probably give it a few more iterations on vision LMs, and these are hopefully problems of the past, and then we can really get rid of PDF to Markdown. Great, thanks so much, and yeah, looking forward to questions.
Thank you. Thank you. So it sounds like for text, you can do something that's like top 50 text chunks, but if it comes to images, maybe you can only do one or two before things get pretty confusing. One question that really stuck out to me was actually a question that is what are the most important evaluation sets or metrics that you look into these days? And like in terms of how you prioritize improving these metrics, like what would you say are the biggest ones? Is it just hallucination rate? Is it something else?
For retrieval or in general, like text rec?
I would say for retrieval for now, just because I think most people are curious about
Yeah.
that.
Um, yeah, I mean, for retrieval, you typically use NDCG at 10. So you say, okay, this is your query, this is a document, these documents are relevant. And then you typically optimize for NDCG at 10. You can also optimize for others like recall at 10 or recall at 100. But often the correlation between these scores is like very, very high. And what we do is like test very, very broadly. So many people fall into the trap to very narrowly tested. So there's like others like Colquent, Cold Poly, GME, for example, who are also doing like vision retrieval. They test like very, very narrowly. Like they
Mhm.
just test if your page has kind of like black text, white background, and is letter sized. But then in reality, you have like people have an image like this, or an image like this, or it's rotated by 90 degrees. And then all these models really fail on it. And so for us, what we do is like we test long tail, like really say, I don't know, whiteboards. We got like a bunch of whiteboards and say, okay, like what are like good queries on it? Can we find the right information? Handwriting, can we do like the handwriting on these?
Mm.
Found like supermarket. It's one of my favorite. It's Hungarian prospects for supermarkets like Aldi and so on and Trader Joe's to say, okay, like where do I find the bananas in these prospect and who has like the best deals on bananas? And then it looks in Hungarian on these supermarket advertisements, prospects with all the special deals for this week. And this gives you like a very, very robust um, models. So most models, they work well on like these MS Marco style or MTAP beer style, like very short. MS Marco is like 50 tokens
Yeah.
on the query side. There they work well, and then people kind of like battle on it. But in reality, in many enterprise use cases, you have something like this that you say, okay, we have, I don't know, million scanned documents from a lawsuit with handwriting, and we need to index that and search over it. And then you want more like a general purpose model.
I guess here's a question. I think many people are actually asking a little bit more about like what Cohere Compass is. I'm curious, like for something like Cohere Compass, like are you still blending things like, full text search? Like how does that architecture really work? And I think a lot of people are curious about what the actual end-to-end product looks like.
Yeah. Um, so it's an on-prem solution for intelligent search. Um, it solves multiple things. So first in enterprise, solve the connector issue. So in an enterprise, you have your data in all different type of locations. For example, you have it like in a SharePoint and in Microsoft Teams and in your Gmail maybe. So it connects to these data sources, pulls the data from there, synchronize it with a vector database, and also implementing the security and role permissions. So like if I put my emails in it, only me should be able to read the emails and not my coworkers. Similar in SharePoint, you have like these, oh yeah, this is like a private SharePoint. What's a SharePoint just for the team? Like, how do you ensure this security that really data is not leaked, like that you can't go to like the RAG system and ask like, hey, what is my manager thinking about my performance? Will I get a raise? And then it's looking into the inbox. And then second part, more on the retrieval side, is like understanding the data. So if you connect to a SharePoint, what data is in there? Is it a text? Is it a PDF? Is it an Excel? Is it a video? Parsing the image, blending text and images together. Because in many cases, pure vision RAG is still too limited due to these shortcomings. So you want to kind of like when the PDF is text, you want to put it as a text. But if the PDF has like complex visual elements, you want to put it as a complex visual element. So kind of like does the pre-processing, creates like the optimal representation for an LM. And then using different retrieval strategies to find information, like how do you search on tables, how do you search on invoices. Um, so it's like a nice all-in-one solution you can deploy, put your data in, and get the right results out.
I guess to talk a little bit more about that, like what has Cohere really learned about, these like chunking techniques? Is it still just the case that you have some kind of like 800 token sliding window, 50% overlap? Are you thinking about things like contextual retrieval? Obviously, there are like image boundaries and caption boundaries, but I would love to learn more about how you guys
Yeah.
are thinking about that.
Um, so yeah, in terms of chunking, let's say if it's a PDF, page level chunking works quite well.
Mm.
because humans, they typically spend a lot of time to create like a nice PDF to adhere to page boundaries. So like seldom you find like a table that goes over like 2 pages, but it's mostly like one page. We contextualize the information. So if you just look at like a random page in a PDF, it's like very hard to say what's in there. So we go in, contextualize it. Um, Challenge on the contextualization is like how to scale it. So it's if you go like these entrophic contextualization, it's okay if you do it maybe for 1,000 PDFs, but some customers
Right.
have a billion PDFs, and then it becomes very slow, expensive to contextualize it. So highly efficient contextualization. And then, but we're also tapping into more of like these understanding um, agentic use cases. So sometimes you find in a PDF that it says you can find the parameters for the model in Appendix A. And so that's a chunk. And then if you
Uh,
say, oh, what was the parameters for this model? And then you retrieve the chunk like, oh yeah, you can find the parameters in Appendix A. You say, oh yeah, that's nice to know, but it's not really helpful for RAG. Like for a human, it's okay because we read it and then we jump in the PDF. So we're working on like how can the AI, the LM, like jump in the PDF. So if it reads like, oh yeah, the interesting details are in Appendix A, how can it jump to Appendix A and get the information from Appendix A as well?
and in those situations, is it going to be the case that we've somehow resolved Appendix A to some other text chunk, or is it very much like, oh, our agent should have the grep tool and it should just grep for like Appendix A lowercase and
Yeah.
find there.
Um, yeah, we're working on that. So uh, not sure what's like the best tool, um, because again, PDFs can be very diverse. So some PDF has like a digital table of content in it. So you see like all the text, you see all the chapters and sections, and you know the pages, and then you can jump to the right pages. But some PDFs don't have it, or even worse, some PDF has like have it like a misleading table of contents. Sometimes you can grab, but then the challenge can be like, say the section title is not as a text, but it's maybe like an image. So they put like into like a very nice font, render it in Adobe Photoshop and put it as an image. Um, but yeah, it's mostly what works is if you have like a good search system, you say, okay, you put a filter and say, okay, only search on this PDF, and you search for like Appendix A. And then you hope that the search system is retrieving the right Appendix A, but it might be that it retrieves chunks where it's also referred to Appendix A.
See, I see. That makes a lot of sense. Yeah, I think in a lot of the coding agents, grep probably works a lot better, but I can imagine half the text being images is probably going to make it very hard. I think a lot of questions here are also asking about the synthetic data and data augmentation. Like how much, I can imagine a lot of the translation, for example, could be multilingual, could be like machine translation, but um, how are you thinking about the investments you're making in data augmentation and synthetic data generation?
Um, yeah, so a challenge here really on the region domain was like getting the data. Like for text, it's easy to find like these question answer pairs for text. You go to like Stack Exchange, you get the questions and the answers from Stack Exchange, Stack Overflow, and this gives you like 100 million, 200 million question, like question title, question body, and different answers with different upvotes. And but you seldom see this for images. Like no one is really asking question at a large scale and then say, okay, this image is relevant and has the right information. So no one has like these, what's the market share for AWS? And then I get like this as an image, as an answer, or even worse for like a PDF page. No one is asking question about Siglip. And then you say, oh yeah, this page for Siglip is relevant. So we
Mhm.
spend a lot on like data augmentation, synthetic data generation. Um, can be we kind of like went to LaTeX. So we created a bunch of different LaTeX styles. We put standard benchmark, let's say from beer into LaTeX, rendered it in LaTeX with different font sizes and colors and layouts. So let's say 1 column, 2 column, 3 columns. And then you get like a very nice comparison. So let's say you take the natural questions data set from beer, and then you render it in all these different styles. And you know, okay, if I do text-to-text search, that's my performance. If I do text to image search and the image is, I don't know, gray text on white background with font size 4, that's the performance. And then you see kind of like what's the delta between these. Same with multilingual. So you machine translate it to other languages for testing. Um, a lot of crawling, finding interesting data sets. So finding PDFs in Arabic, in Korean, in Japanese. Looked for like where do you have these information, looked for like parallel information. So for example, stock companies, they often put out annual reports in English and then the identical report in Arabic, for example, and then collected these from, let's say, Saudi Aramco, where we say, okay, this is a report in English, that's the same report, every page aligns in Arabic, and
Mm.
then you use it for evaluation and testing. Wikipedia also kind of like go to Wikipedia and then print Wikipedia. So you call a Chrome, you say print it to PDF, and then you convert the PDF to images. And then you have like the raw Wikipedia and you have the printed Wikipedia of the same article. And then you can ask questions on it, or in a browser, you render the full Wikipedia as like one long image. And then you can ask like a question, like, I don't know, you zoom in and say, okay, for section 5, you ask like, I don't know, what was Barack Obama's favorite sports in primary school? And then on the other side, you have like the full rendered Wikipedia page. And then you use this for training and evaluation. So it's a lot of synthetic data generation, a lot of creativity. So many people fall into the trap to have like this one pipeline. So if you look also at like Colco and Copali, it's like these, or Vidori, it's like these one pipeline they use to create data for training, and sadly use the same pipeline for evaluation. And then it only works on really this one setup. But I think the key is really this diversity of training, diversity of evaluation.
I see. That makes a lot of sense. I was gonna ask a question like, given how these transformers have to unwrap images to a sequence of tokens, like how does it handle like multi-column layouts? I think in Japanese, sometimes it's top down, sometimes it's left right versus right left. But it sounds like the answer is just if you create enough data, you can just be robust to all of that.
Yeah, I mean, especially if you have like these patches,
Hmm.
can be that an image is what a character, a word, numbers broken into like multiple patches. So here we see, for example, like the human is in patch B and patch E. And this happens also with characters that like they are like on these boundaries. And maybe these characters are like very critical. And it's like, yeah, so you need a lot of data to really robustly so that the model knows, oh yeah, like the character or the word can be in patch B, C, and E.
Yeah,
So that the model knows and it's not confused that the information is split across these different patches.
makes sense. I mean, we have 7 minutes left. I guess the only question I'll ask now is, what is one question you wish we asked you?
Oh, that's a good question. I don't know.
Okay. In which case, I think I'm gonna pull in one question from the topic. I think there was a lot of people asking about um, the voyage models versus the voyage multimodal models versus the embed four models. Like, how do you think about, what the similarities are, what the differences are? Is it an
Yeah.
architectural thing? Yeah, I'd love to learn more about that.
Um, yeah, so I don't know the internals of the voyage model, so it's just speculation and what we see from benchmarking. What do we see from voyage multimodal is more, it feels more like these traditional approach. You have a text model, you have an image model, you align them. Where we see it struggles like understanding these more complex images, and it also struggles in like when you interleave text and images. So let's say you have like a Jira ticket, a GitHub issue, someone is writing a text and then posting like a screenshot with the error message and then writing more text. This is like something we specifically train for, like take GitHub issues where you have text and images interleaved and you ask questions that address text and images. That works well with Cohere Embed 4. That doesn't work well with Voyage multimodal.
Makes sense. Great. I think that's all. I have another presentation in 5 minutes. I think we can get some time back as well. Nils, thank you so much for this. I learned a lot. I'm definitely gonna start asking you questions about the audio and video embeddings at some point because it sounds like it might be more of an audio tokens situation rather than like a transcription. So I'm pretty excited to see what that looks like, and maybe I can start doing like music search applications in
Yeah,
code.
hopefully
Okay.
that's the goal.
Yeah. So for everyone else, I think if Nils is okay, we'll share the slides afterwards. We'll share the video and the recordings with some study notes, and then we'll share more information about uh, the program, the cohort, and what we have for next week. Great. Thank you so much. Thank you,
Great
everyone.
to be here. Thank you. Bye bye.
Take care, everyone.